one of the most curious properties in mathematics is that math does an amazingly good job of describing the real world while being completely and totally made up. We made these ideas from whole cloth. It's a rather famous quote. God created the natural numbers, the rest is the work of man. We built all this garbage, but it works in describing the real universe very, very well. So in any given situation, there's some underlying math there, and if something is changing in that situation, there's calculus hiding there. I started as a science geek, physical chemistry and physics. So let's start there. I have a cart on a track. Its position at any given time t, measured in seconds, is s of t. A direct question I can ask then is, how fast is the cart moving? And then I can pick a time. How about at time 4, time 2? How fast does this thing go? First of all, how do I find how fast, period? Before I even worry about putting in times, 4, 2, how do I figure out how fast the cart is moving at any time? Fiona? Because this is position, change in position is exactly what speed, how fast is measuring. So I want velocity. That's my derivative, which in this case is exactly a quadratic. And now I can plug in the times that I want. If I want how fast is the cart moving at 4, I want v of 4. At 2, I want v of 2. So give me some numbers and units. I'm in need of numbers. What's V of 4? See? 3 times 16 is 48. Minus 48, those cancel, and I get 9 meters per second. At time 2, three times 4 is 12, minus 24, that's negative 12, plus 9 gives me negative 3. Okay, hang on a second. What's positive or negative mean in this interpretation? What does it mean to have a velocity of 9 meters per second? I'm moving forward in the same direction in which the distance is measured. And then the negative one means I'm working backwards. Given the orientation I've set up this picture, I would say forward is to the right and negative is to the left. But that's an arbitrary decision. If I'm sitting in the cart, maybe it's forward. Right? It's now dependent on the interpretation of the physics of the situation. But having the numbers positive and negative means I need to interpret that appropriately. When's the cart come to a stop? If I am not accelerating, when the velocity is 0. Because if my velocity is 0, I shouldn't be moving. If I'm not accelerating, then I'm going to be moving at a constant speed. Force equals mass times acceleration. If no acceleration is acting on a body, it remains at the speed it was going, right? A body at rest remains in rest. A body in motion stays in motion. The other one of Newton's laws. So I need where my velocity is 0. Well, I'll take my derivative, set it equal to 0. Easiest thing to do is divide by 3, since everything there is divisible by 3. Because that quadratic's easier to deal with. Smaller coefficients are always better. And now you have a choice. Factor it, quadratic formula, complete the square. I don't care how you decide to solve this, but you need to solve this quadratic equation. What do you get? Before you give me your answer, go back and look at those velocities. At time 2, moving to the left. Time 4, I'm moving to the right. Yes? Somewhere in between, what did I have to do? Stop and turn around. So one of the numbers you come up with better be between 2 and 4. And is it? Yeah. I get 1 and 3. T minus 1, t minus 3 factors this. So I came to a stop at 1 second and at 3 seconds. Question. How far do I go in the first, say, 5 seconds? How do I figure out how far I went in the first 5 seconds? That will tell me where I am at 5 seconds, right? S of 5. I apologize for having S's and 5s in the same problem. Where am I at that point in time? Say that again, B? Or do S5 minus? That will tell me how far I have moved from where I started. There's just one problem. If I do S of 5 minus S of 0, S of 0 happens to be 0. All that tells me is that I started here and ended here. But what does this tell me? At some point I was moving backwards, wasn't I? So I didn't just go from there to there. I went back and forth. If I hit a home run, start at home plate, end at home plate, I didn't go anywhere, did I? If I didn't do all the way around the bases, they're going to tag me out and I don't count. So this is the displacement. It isn't the distance traveled. If I want the distance traveled, I need to take into account every time I came to a stop and changed direction. Because really, I came to a stop at time 1. Where was I at time 1? Where am I at time 1? I'm at 4 meters. And at time 1, I moved to the right, but I came to a stop. I know at time 2, I'm going left. So I had to turn around and start going back. I came to another stop at time 3. Where am I at time 3? I'm back at 0. 27 minus 54 plus 27 puts me right back at 0. And I'm only counting till time 5. So even though I'm not stopped at time 5, from time 3 on, I'm moving to the right. So really what I did is I did this. And if I want to know the total distance covered, I actually have to count that left piece 3 times. I went back and forth here a bunch, didn't I? So really, it's not S of 5 minus S of 0. It's S of 5 minus S of 3 in absolute value. Plus S of 3 minus S of 1 in absolute value. Plus S of 1 minus S of 0 in absolute value. The absolute values is because distance doesn't care whether I'm moving to the left or the right. It just cares how far you go. This is why even when you put your car in reverse and back up, the odometer doesn't roll backwards. If I back up 3 kilometers, it doesn't look like I've driven 3 less kilometers than I did driving forwards. Matter of fact, when you back up, it rolls the odometer forwards. So this gives me 20 plus the absolute value of -4 plus 4 for a total distance traveled of 28 meters. Questions? Yes, ma'am. Because I didn't come to a stop then, right? If I'm still moving, I really don't care how far I've come until I stop and turn around. I could make as many other divisions as I want, right? How far do I move from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, right? I could absolutely do more, but I only need to follow those line segments for the motion I'm actually covering. Make sense? More questions? Cart's moving. And it comes to a stop at 2 different points in time. If it came to a stop at 2 different points in time, it had to be slowing down at some point. How do I know when an object is speeding up versus when it's slowing down? Oh, wait a minute. This is change in velocity, isn't it? Change in velocity is acceleration. That's a second derivative. It's the change in velocity, so it's S prime prime. So I need a second derivative. Okay. I want you to graph for me. I want you to graph the acceleration and the velocity. And to make my life easy, let's only worry about graphing between times 0 and 5. So our velocity equation was 3t squared minus 12t plus 9. But if I'm graphing, I'm going to change all of those to x's. And then my acceleration, 6x minus 12. Now, I only care about the time window we were looking at, so I'm only going to put 0 to 5 on here. With me so far? That makes sense. My graph of my velocity is a parabola, 3t squared. And there's my acceleration. Okay. So let's think about what's happening at different points in time here. Between time 0 and time 1. Which graph is which again? One of those is velocity, one of those is acceleration. If you've got a color calculator, it'll be easier to deal with. I have this old black and white one. Which one's which? And that one's on the top. And acceleration is the line, and that one's on the bottom. So during this time, my velocity is positive. I'm going to the right. But my acceleration is negative. It's to the left. So we are moving this way and being pushed that way. So what happens to my speed? My velocity is going down. Between time 0 and 2. Sorry, between 1 and 2. I'm now moving to the left. And my velocity is moving to the left. And my acceleration is pushing me to the left. Those are both negative. Look at my velocity. My velocity gets more and more negative, doesn't it? I'm doing -0, doing 0, then I'm doing -0.1 or -2 and -3. I'm getting more negative. That means I'm moving to the left faster and faster and faster. Until time 2, when my acceleration changes and becomes positive. So between times 2 and 3, I'm moving to the left, but I'm being pushed to the right. What happens? I slow down again. Does this make sense? I was going to the right, and then I came to a stop. I have to slow down and come to a stop. Otherwise, I break the cart. And I start moving to the left. I speed up, and then I slow down so that I can come to a stop again. And then I start moving to the right, and both of these are positive. So I am going to the right and continuing to go faster and faster. Oh, they're not matching. Opposite. If they're matching, I'm going to speed up. If they're opposite, I'm going to slow down. And I can literally just make a timeline. 0, 1, 2, 3, 4. And then I can write signs for my velocity and my acceleration based on that picture. The acceleration only went from negative to positive at time 2. 6t minus 12 is only 0 at 2, so it's either negative or positive everywhere else. And I see here. Questions? I like physics a lot. Like I said, I was originally a physical chemistry student. So to me, these are the sorts of interesting elementary pieces that we start with. So I have a wire, and I can actually think of the wire as a tube of metal. It's a really thin tube, but it's a tube. And I can think of a slice of that tube. And I can say right here, I can count the amount of electricity in number of electrons. You measure electrical behavior in coulombs. So I have this little spot where I have the number of electrons in that spot. But electricity is electrons moving. Technically, it's electrons moving the other way and the little positive holes that leave behind moving one way, but that's neither here nor there. If I measure the change in current, sorry, the change in charge, that's the current in the wire. Anybody know the units for current? Here's where I get to be really close to the fuse box. Yep, they are like that. This is the only way to turn the air conditioner off in this room, is use the fuses. But the fuses are rated so that they will only allow a certain amount of current through. The bigger the fuse, the more current it will allow through. The smaller the fuse, the less current it will allow through. Literally, when you overload a wire, when you bring too much current through it, the fuse melts. The mystical gray smoke escapes and things stop working. So I want to know how much current is moving through this wire. That's measured in amps. These are all named after people. Coulomb was the person investigating electric charge. Ampere investigated current. Volts are Voltaire. I'd love to tell you I made this stuff up. But those wires back there have 20 amp fuses. They'll only allow 20 amps through before they say, nope, nope, too much, I'm done. But that's really velocity. It's the velocity of those electrons. How fast are they moving? How much current is going through? This is exactly the same as the moving cart. Instead of one cart, I just have a lot of them. In chemistry, I can talk about reaction rates. In biology, I can talk about growth rates. We'll do a whole thing on growth rates when we get back from break. But if I think about the way in which objects grow, I have a petri dish full of stuff. And I measure it, and every hour I notice it's twice as big as it was the hour before. Then I can write this as a doubling function. It's going to double. Where t is in hours, every hour that goes by, it gets twice as big. If I want to know how fast this is growing, well, then I need the derivative. We had a formula for this. There are two different ways to have this formula in your head. This kind of looks like an exponential, right? It's just not e, it's 2. I could convert it to e. How do I switch from base 2 to base e? This was in our chain rule section last Friday. It's also on the formula sheet that's on the review, on the exam review, and will be on the next exam. Formula's on there. I remember that e's and ln's cancel each other out. So I'm going to write this as e to the ln 2 to the t. And when I have a power and then another power, those get multiplied together. ln2 is just a number. 0.693147. I happen to remember that one. That's what happens. You use these enough, you end up remembering some of them. But if that was e to the 3t, and I went to take its derivative, what would happen to the 3? What's the derivative? E to the stuff. E to the stuff. It's not just e to the x anymore. What's the derivative? E to the stuff. So I'm going to get the e to the stuff again. Right. Times the derivative of stuff. So what's the derivative of number times t? What's the derivative of 3t? And derivative of 7t. So the derivative of number t is just number. Wait a minute. This is 2 to the t. Here's that formula sheet with all the trig things on it. Very top. The derivative of a to the t is a to the t ln a. And now you can tell me after how many hours how fast this bacterial population is growing. If I have a particularly virulent infection, I would like to know how fast that infection is going to spread. If the number of bacteria keep growing and growing and growing, I need to know about that. Now, I'm the first to admit, this is an unrealistic model of growth because it assumes there's an unlimited amount of room. Because what's the graph of 2 to the t look like? It's going to go up forever. Uh-oh, that's not really going to work. So there are some limitations to this. That's the thing we're going to discuss in more detail when we get back. The general principle is the same. No matter what formula I have, I can investigate how things change. Here's one of my creepy examples for all of you future forensic people. What's exsanguination? Is a helpful word for you. No? Exsanguination means to remove the blood from. It is commonly used when a massive wound in a body occurs and a lot of blood leaves the body at once. Usually a slashing wound that leaves a large blood splatter all over the walls that all the forensic people get to investigate. I'm not sure if it's the spring or the fall, but at some point when they do the blood splatter analysis class, if you walk down the hallway in Lynch, the walls will be covered with paper and people will be standing there with weapons, slashing at the paper to show you what the splatter looks like coming off of things. It's a very bizarre time to walk down Lynch Hall. However, if I am just looking at a blood vessel, the speed with which blood moves through the vessel, here's my tube again, depends on a lot of things. It depends on the pressure. It depends on the radius of the vessel. It depends on how long the vessel is. It also depends on where you are in the blood vessel. The closer you get to the walls of the blood vessel, the more turbulence there is interacting with the walls of the blood vessel. So the further out I am from the center, let's say I'm only partway out with my little red blood cell, that radius matters too. And one of the more interesting pieces, the viscosity of your blood. That's the Greek letter eta. Looks like a fancy looking N. This is why people take blood thinners. If you make the blood less viscous, it flows better. It's less likely to clot. It's less likely to cause issues. This is why baby aspirin are given to adults who have had strokes or Plavix or any of those other blood thinners that are designed to ease the motion of your blood. There's a really interesting formula here. The velocity at R, where I am in the blood vessel, is given by this really crazy result discovered by Jean-Leonard Marie Poiseuille. And he was actually trying to use the speed of fluid in a tube not to measure blood, but to measure water flow in tubes. Poiseuille visited London and noticed a very big problem in London. London stank. Do you know why London stank? Because the sewers flowed into the Thames River, which went right through the middle of the city. And they would clog up because the Thames was not a very big river in the 1600s and 1700s, and they had to trench it and dig it out repeatedly. And they would measure the fluid flowing through the sewers. How? By taking a pipe open at the bottom and sticking it into the tube and seeing how high fluid came up the pipe. This was then adapted to measure the speed of blood flowing through a body, which would allow me to measure someone's blood pressure. I kid you not. How do they measure your blood pressure today? That lovely little cuff thing, right? A sphygmomanometer. They squeeze it until they stop hearing your blood move through your vessel. Then they open it and they hear the first compression, which is the strong beat of your heart from the ventricles. They hear the second compression as they lower it more, which is the softer part from your atrium. So the two beats of your heart. Done, done. The bottom closing, the top closing. The strong and the weak. Systolic and diastolic. That's what they're listening for. But they needed a stethoscope for that. The stethoscope was invented in the 1700s. Poiseuille discovered this idea first. They would take a sharpened glass tube, jam it in somebody's arm and see how the blood went. Being a doctor was a lot thicker back then. But by using this idea, I could determine where in the tube the blood was flowing, where in the vessel, where in the tubes in the city, the water was flowing properly. And if there was something causing the tube to constrict, if the diameter gets smaller, what happens to my speed? If this number, capital R, gets smaller, this number is going to go down. And the only way to compensate for that, the only way to get the fluid moving at the same speed is to increase the pressure. Narrow arteries, higher blood pressure. They're directly connected. Poiseuille was able to take this idea, apply it to the medical field, and measure changes in blood pressure by changes in speed. I'm much happier with the blood pressure cuff. I don't get stabbed as much to check my blood pressure. Page 232 talks about exactly this model. I don't care what field you're going into. There's an application there. If you take an econ class, you'll talk about a cost per unit. So we can have a function that's a cost function. So I'm the manufacturer of whatever, let's see, the most commonly used things in most econ classes are widgets. We're making widgets today. And if you have a fancy econ class, they'll make baubles. I don't know who came up with this crap. They don't want to give you specific products most of the time. They're worried about trademark infringement. So my widget factory makes X widgets. It costs me however much. If I want to measure the change in cost per unit, C prime of X is the cost change when I produce one more unit at a current level of X. So if I'm making 100 units, I do C prime of 100. That tells me how much it'll be to move to 101 units. If I'm at 1,000 units, I'll do C prime of 1,000. But I need to know where my current production level is. We call this the marginal cost. In general, this should represent the cost to move up one production unit. So if I'm making, I don't know, what am I going to make today? I'm making guitars. And I can make 15 guitars a day in my factory. If I want to move from 15 to 16, the cost increase should be C prime of 15. Which means here's my cost function. If I do C prime of 15, you can figure out how much my costs will go up. If I tell you, no, I need you guys to make one more guitar a day. This should be roughly equal to C of 16 minus C of 15. Roughly. If I am at a production level of 500 and I do C prime of 500, that should be roughly the difference between the cost at 501 and the cost at 500. If I can do it for cost functions, I can do it for revenue functions. If I can do it for revenue, I can do it for profit. Marginal analysis is all about, in business, figuring out the right way to determine optimal costs, optimal passing on of cost increases. Fiscal policy, like tariff policies, that was just invalidated by the Supreme Court a couple of weeks ago, or tariff policies implemented by the president, cause changes. How much of that cost should I send on to the consumer? How much of it should I eat? Where's my maximizing my profit as opposed to examining strictly cost or revenue? This entire section contains a lot of examples. And the advantage is that all of them are derivatives. Vibrating springs in a violin, yeast cells in a laboratory, reaction rate in a chemical. Which problem is this one? I ate it. There we are. Problem number 23. We've gotten to the point. We do some of the most amazing stuff here. It turns out that one of the side effects of moving really, really, really fast is things get harder to measure. If I have an object that's moving really fast, how do I figure out how long it is? Well, I measure the front of it, and then I look to the back and I measure the back. But if it's moving really fast, by the time I've looked at the back, it's moved. It gets shorter. This is called length contraction and is a problem in relativity theory. Force equals mass times acceleration. It's harder to accelerate something that's already moving fast. The faster you go, the more energy it takes to accelerate. This is why we can't go infinitely fast. It just gets harder and harder and harder to move. how much harder? That probability is about relativity theory. Congratulations, you actually are doing rocket science. I will see you all after break. Have a wonderful break, everybody.